Welcome to YouTube channel scientific_math. In this lecture, we discuss the mean value theorem. Learning objectives: number 1, explain the meaning of Rolle's theorem. Number 2, describe the significance of the mean value theorem. Number 3, state 3 important consequences of the mean value theorem. In this lecture, we discuss point number 1, explain the meanings of Rolle's theorem. We also proof of this theorem, and we will solve some examples related to Rolle's theorem. So let's start lecture. Rolle's theorem. Rolle's theorem states that Rolle's theorem states that if the outputs of a differentiable function f are equal at the endpoint of an interval, then there must be an interior point C where the derivative of this function is 0. We have already discussed about the differentiability and the continuity of the function in previous lectures. I will provide the link in video description. You can watch. We know that if the function is a differentiable function, then it is also a continuous function. Okay, so this is the meaning of the Rolle's theorem. If we have a function that is differentiable and the value of the function at the endpoint of the interval is the same, then there exists at least one interior point C on which the derivative of the function f prime of C will be equal to 0. Okay, so we can see with the help of graph, if we have a function like that and the value of the function at the end point of the interval is same, we can see that at A the value of the function is this, and at B the value of the function is this. Both are the same. Okay, then there must be an interior point C on which the derivative of the function is equal to 0, and the derivative of the function means 0. This mean and the slope of the tangent line is equal to 0. Okay, this implies the derivative the slope of the tangent line will be parallel to the x-axis. Okay, and at this point we have absolute maximum. Okay, next, if we have a function like that and we can see the value of the function at the endpoint of the interval both are same, then there must be an interior point C on which the derivative of the function is 0, and derivative of the function is 0 means first derivative 0 means and the slope of the tangent line is 0, and we can see and the tangent line is parallel to the x-axis, and at this point we have an absolute minimum. Okay, next, if a differentiable function f satisfies this criteria, the value of the function at the end point of the interval will be both are same, and then its derivative must be 0 at same points between between A and B. Okay, so this is the meaning of the Rolle's theorem. Now we prove the Rolle's theorem. Okay, theorem, let this is the statement of the theorem: let f be a continuous function. Okay, I have already told you about the continuity and differentiability of the function. We have already discussed in previous lectures the continuity and the differentiability of the function. Again, I will provide the link in video description. You can watch. Okay, so let f be a continuous function over the closed interval. This is our closed interval or bounded interval, and differentiable over the open interval, and such that and the value of the function at the end point of the interval is same. Okay, there exists at least one C that belongs to open interval, and such that the derivative of the function at C will be equal to 0. So let's start the proof of the theorem. Proof of the theorem, and first we consider let k is equal to f of a and f of b. This means the value of the function at x is at a and b both are same, that is we take some constant k. Okay, so we consider here three cases. Number one, the value of the function at x is equal to some constant k for all values of x. This means we have a constant function like that, and for all values of x we have a constant function, and this is a and this is b, and the value of the function at a is equal to this one, and the value of the function at b is equal to this one. Both are same. Okay. Number two, there exists at x belongs to the open interval a b such that the value of the function at that x is greater than k. That is our value of the function at the end point of the interval. And number two, there exists x that is belongs to open interval such that the value of the function at that x is less than k. This is our the value of the function at the end point of the interval. Okay, we can see here if we have the value of the function at that point, and then the value of the function at x is less than k in this case. Okay, here this is our k, we can this is our we can say this is value of the function at x, f of x. Okay, so we can see at this point, and this is, we can say this is not x, this is not c, this is x, and at this point x, the value of the function is less than the value of the function at the end point of the interval. And in this case we can see if this is x, and at this point the value of the function is f of x, and the value of the function at the end point of the interval, here we can see the value of the function at the end is greater than the value of the function at the end point of the interval. So we discuss all three cases one by one. Let's start. Case 1, if the value of the function at x is equal to 0 for all x belongs to the open interval, then the derivative of this function is also 0 for all x belongs to the open interval. Like that, if we have a constant function, and the value of the function for all x is like that at this point, so we can see if we have a constant function like that, and the derivative of the constant function is 0 everywhere on the open interval. Okay, next case, case number 2, since f is a continuous function over the closed interval or the bounded interval, then by extreme value theorem it has an absolute maximum. Okay, so since there is a point x belongs to the open interval such that the value of the function at x is greater than k, okay, and the absolute maximum is greater than k, yes, therefore the absolute maximum does not occur at either end. Okay, at the other end point, yes, as a result the absolute maximum must occur at an interior point, and interior point is c, that is belongs to the our open interval. Because f has an absolute maximum or maximum at an interior point c, and f is a differentiable at c, then by Fermat's theorem, and the derivative of this function is equal to 0. In previous lectures we also had proves the Fermat's theorem. I will provide the link in video description, you can watch. Okay, now we see this with the help of a graph. If we have a function like that, and the value of the function at the end point of the interval both are same, okay, then there will be a interior point on which the derivative of the function is 0. And yes, in this case we can see the value of the function at that c is greater than the value of the function at x, because this is the value of the function at end point of the interval, and here the value of the function at the interior point which is greater than the value of the function at the end point of the interval. Here we say this x is equal to c. Okay, this means at this point we will have a absolute maximum. Okay, and at this point the derivative of the function is 0. That is the Rolle's theorem says that if the endpoint of the if the function has same values at the endpoint of the interval, and then there will be one interior point, at least one interior point on which the derivative of the function is 0. Okay, so the first derivative 0 means the slope of the tangent line is equal to 0, and here the tangent line is parallel to the x-axis. So this is the case 2. Now we discuss case 3 when the function is when the value of the function at x, that is less than k, means less than the value of the function at the end point of the interval. So then this x will be our interior point, because we suppose because here we have x belongs to an open interval. So the absolute minimum is less than k. This means the absolute minimum is less than k, and k is the end point of the interval. K is the value of the function at the end point of the interval. So therefore absolute minimum does not occur at either end point, because we consider case here x belongs to an open interval. So this means the absolute minimum does not occur at either endpoints. Will be absolute minimum will occur in some inside the interval. Okay, next, as a result the absolute minimum must occur at an interior point, that is c belong to open interval AB. Okay, because f has an minimum at an interior point c and f is differentiable, then by Fermat's theorem we can say that the derivative of this function at this point is 0. Now we see this with the help of graph. Suppose we have a function like that, and the graph of the function is this, and we can see the value of the function at the end point of the interval both are same. This means there must be some at least one interior point belongs to an open interval belongs to interval AB, on which the derivative of this function will be equal to 0. We say this x is c. Okay, so this is our interior point, and this is c, and at this point the derivative of this function is equal to 0. First derivative 0 means the derivative first derivative 0 means the slope of tangent line is equal to 0, and the slope of tangent line 0 means tangent is parallel to the x-axis, and at this point we have an absolute minimum. Okay, and in this case the value of the function at c is less than at c, or we can say at x is less than the value of the function at the end point of the interval, and the value of the end point of the interval is k. Graphically we can see this is the value of the function at the end point, and this is the value of the function at the end point of the interval, and here c is less than, so here c value of the function at c is less than the value of the function at the end point of the interval. So this is the proof of the Rolle's theorem, and now we discuss some examples related to Rolle's theorem, in which we will see if we have a continuous function on the closed interval and differentiable over the open interval, then the value of the function will be same at the end point of the interval, and there will be at least one point c, that is our interior point on which the value of the function on which the value of the derivative of the function will be equal to 0. Example: verify that the function satisfies the criteria stated in Rolle's theorem and find all values c in the given interval where the derivative of the function is equal to 0. So this is our given function. X square is x square plus 2 x over the interval closed interval minus 2 0, and let's start the solution of this example. Okay, and we know the given function is polynomial, so it is continuous and differentiable everywhere. First step we evaluate the function value of the function at the endpoint of the interval. Okay, x is equal to minus 2 and x is equal to 0, so the value of the function at x is equal to minus 2 is 0 and at x is equal to 0 is 0. Therefore this means the value of the function at the endpoint of the interval both are same. It's mean there will be a interior point on which the derivative of the function is 0. Okay, and therefore f satisfies the criteria of the Rolle's theorem. Okay, step 2 we have there exists at least one value, and that is c belongs to our open interval and such that at this point the value of the function is 0. First we calculate the derivative of the given function, and that is our given function, and the derivative of this function is f prime of x is equal to 2x plus 2. Now we put f prime of we put x is equal to c, yes, then we put f prime of c is equal to 0 to calculate the interior point c. Okay, and after doing some simplification we get the value of c, that is minus 1, and this minus 1 is belongs to our open interval. This will be a open interval. Okay, and at this point the value of the derivative function will be 0. Okay, so put this c is equal to c minus 1 in this the derivative of the function, and here after substituting the derivative of this function at c is equal to minus 1 is 0. Okay, this means this is our interior point, that is the c is equal to minus 1. So let's see graphically. This is the graph of the given function f of x is equal to x square plus 2x. Yes, and the value of the function at the end point of the interval is 0 at x is equal to minus 2, and the value of the function is 0, and at x is equal to 0 the value of the function at 0 is 0. So this is our second point, and here we have a c, that is c is equal to minus 1, and at this point the value of the derivative of this function is yes, is 0. Okay, so again this is a tangent line that is parallel to the x-axis when the first derivative 0 is equal to 0 means the slope of the tangent line is 0, and the slope of the tangent line 0 means that is parallel to the x-axis. So this is the mean value this is the Rolle's theorem, and in the next lecture we discuss one more examples related to Rolle's theorem, and then we move toward our second point, that is the mean value theorem.